SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. We will continue discussing on the topic of metamorphogenetic hydrothermal system, and the most studied and the most important one are the deposits which are associated with granite greenstone terrains occurring as lode type gold deposits in almost all the old cratonic blocks, like the Ilgarn Craton in Australia, the Barberton Mountain Range in Africa, Dharwar Craton in India, Superior Province in Canada in the Abitibi Greenstone Belt. And in this context, we are discussing about the model that was proposed for these type of deposits to explain the formation of such kind of lode gold deposits in diverse type of lithologies, the most important ones and the most common ones being the quartz rich lodes, in which gold occurs as either free gold or as inclusions in some sulfide minerals, either pure gold quartz lodes or associated with sulfides of copper, iron, and sometimes very rarely arsenic, antimony, mercury type of metals. So we would like to have a look about discussing about the model. So this model explains the diverse lithologies in respect of occurrence of gold in these terrains. So the translation of this model to the occurrence of gold in these terrains can be observed in terms of their occurrence in what we know as the greenstone belts, old greenstone belts, which are mostly Mesozoic age, and they are mostly metamorphosed volcanosedimentary sequence, the old volcanosedimentary sequence, which are known as the greenstones. These greenstones, specifically the greenstones, the ones which start from very high MgO bearing basalts, which are the comatiites, and give rise to sequence of tholeiitic basalt, and the sequence evolves with bimodal volcanism, chemogenic sediments such as the BIFs, clastics, and felsic volcanic units. And these greenstone sequences, which are essentially ocean floor volcanism and giving rise to the volcanosedimentary sequence, they get after the closure of the basins, they are subjected to deformation and metamorphism of high grade, high temperature, low pressure kind of metamorphism. And what we observe them in the greenstone belts, they are mostly as the amphibolites, and they occur as curvilinear or belts extending for several kilometers in strike length and extending deep for even a few kilometers. And these are associated with crustal shell shear zones, which are the locales on which we see the quartz, gold bearing quartz lodes, and these terrains are understood to have evolved through a series of deformation episodes, almost 4 to 5 such deformation episodes, and these terrains have one thing is common, that there is extensive granitic activity, and they do overlap in time with this period of metamorphism and the mineralization, and so that is how the granite greenstone terrain. And so these gold occurrences are confined to such kind of greenstone belts in most of the cratonic blocks, and they give rise to huge quantity in terms of even some of the deposits which are called as giant gold deposits, like the one in the Abitibi province in Canada, and in other parts also they do have substantial quantity of gold present in the form of these lodes, and are of variable grade in terms of the grams per ton, going when in the superficial part or the shallower part, the grades usually are very high, and they generally die out to values as low as even 2 or 1 gram per ton in greater depths. So this model is as a working model which explains the formation of the gold deposits, and the basic mechanism is that the transportation of the metal in appreciable quantity in a fluid which is essentially derived by metamorphism of this volcanosedimentary sequence, especially the units like this the basal unit, which is the comatite basalt, which is supposed to have a higher concentration of gold compared to the other litho units, gold being a compatible metal. But the model of course proposes that there is no litho unit which needs to be having a higher concentration of gold, because the capability of this fluid which is liberated during the process of metamorphic devolatilization is efficient enough to carry gold in substantial concentration, and popularly held belief is that the maximum amount of gold is deposited after the amphibolite greenschist transition, and that is how the deposits are mostly the rich deposits are observed in the shallower part, although mineralizations with a continuum up to higher amphibolite or even granulate grade is also observed in some of the deposits. So this is one of the examples where the mineralization can be ascribed to a fluid which has its origin in metamorphism, although there are many hypotheses involved or many opposing views which are proposed, which I will not be discussing in details. Other deposits which are there will always lack a very ubiquitous, very unequivocal evidence of metamorphic fluid, or as we in the beginning when we were discussing about the sources of fluid and the hydrothermal mineralization process, we often see that mineralization process results from mixing of fluids of diverse sources. So there are other deposits which possibly have or owe their origin to metamorphism, but then the mineralization process sometimes is dominated by other fluids, and those cannot be exclusively called as the metamorphogenic model, metamorphogenic deposits. And then so this is all about the basic idea that you could have without getting into any of the opposing hypotheses or the controversies, because these deposits are one of the most extensively studied, most widely studied across continents, and the amount of information generated on these deposits is quite voluminous, with the fluid characteristics, with the deformation, with the genesis of such deposits. So now I will switch over to a new class of deposit, which are they are also a very important source of gold. These are the Carlin type gold deposit, and here there is a map of the western United States of the state of Nevada, which has been magnified here. So these deposits we could see is a classic gold belt in the Western American Cordillera, and is deposits are essentially associated with a sedimentary sequence, although the fluid that caused the mineralization is not necessarily a sedimentary or a connate fluid, but it's one of the most complicated, most intricate and one of the most complicated deposit types. But they are the rich gold occurrences which are very much sought after. Very active exploration goes on in this region for discovery of new deposits. Some of the localities like this Carlin and all these areas in Nevada, this constitute the major occurrences of Carlin type of gold deposits. So, they occur in marine sedimentary sequences. These marine sedimentary sequences are Paleozoic sequences formed in an accretionary zone, and during the Paleozoic and post, they were all then after the deposition of these Paleozoic sedimentary sequences, they were subjected to compressive regime, and they were intricately thrusted during the Mesozoic tectonism, and they acquired a very intricate Mesozoic tectonic fabric. And essentially the sequence is marine sedimentary sequence consisting of argillaceous and calcareous rocks. And then in the post Mesozoic, this terrain experienced magmatic activity in the form of intrusion of some of the felsic rocks in form of stalks as well as dikes, broadly granitic in composition. And here in these, the specialty of these deposits the gold occurs extremely fine grained nature associated with silicification and quartz veining. The mineralization essentially is by replacement of these calcareous rocks by silica, which is termed as jasperoid in these particular types of deposits. And gold occurs as thin coatings on pyrite on surface of amorphous carbon and also dispersed in auriferous pyrite and realgar. Here the ore fluid is essentially a low saline carbon dioxide containing and H2S containing fluid, which resembles sometimes to some of the epithermal mineral deposits, but they are being classed as their individual type, which are named after most of these deposits were studied and their distinctiveness were brought out. Clearly there is a role played by the late granitic intrusives. So, the mineralization is either proximal or distal to these intrusives, and the fluid inclusion evidence clearly indicates the involvement of meteoric fluid and with the magmatic component also present. These two diagrams depict the sequence, the model, the hypothesis on the origin of the Carlin type gold deposits. As you could see here, it almost resembles, it is a very intricately deformed sedimentary basin where there has been very high angle faults, high angle normal faults, and these are the domains in which the early replacement of the carbonaceous rocks by silica and jasperoid replacements took place, and there were intrusion of the felsic magmatic body, granodioritic intrusion in forms of stalks, and immediate vicinity of these stalks there were stockwork type of veinings and formation of the calcilicate type skarn, and there were these intrusives essentially made these intrusives also contributed the magmatic fluid at the initial stages. So, the initial mineralization was more of a skarn stockwork type in the immediate vicinity of the intrusives, and with later progress into the later stages, the distal Carlin type replacement deposits started to form in these regions, which guided very much structurally controlled, and these are close to or distal to the intrusives after the basinal fluid was replaced by deep circulating meteoric water. So, these with the heat provided by these felsic intrusives, it set up the convective circulation convective flow of the meteoric fluid, and it is believed that gold and the fluid in terms of sulfur and the complexing species were contributed by this felsic magma, and these mineralization resulted, and this is tentatively, or this is a very simplistic way of presenting the origin of this kind of very important class of deposits. They are not only confined to the Carlin they are not mostly confined to these western United States. There are similar type of deposits which are also reported elsewhere. So, with the discussion on the Carlin type deposit, which are one of the very special type of deposits, a very special type of hydrothermal system, we would now go over to discuss another very special type of hydrothermal system, which is the iron oxide copper gold system, and it is actually this particular class or this particular group of deposits were named or started to be investigated in more details after the discovery of this Olympic Dam deposit, which can be told as one of the major discoveries of the recent past in the history of mineral exploration, where a huge concentration of copper, gold and uranium was found in a body of granite, which is essentially within a zone of which is brecciated. In this zone kind of a brexia complex, almost going to the order of gigaton quantity of the metals, copper, gold going to 0.5 gram per ton grade, copper, and massive uranium mineralization was observed in one of the associated with this brexia complex within the within the rock the granitoid in the Gawler Craton in South Australia. So, this is a very important discovery in the recent past, and it gave rise to a new concept of ore deposits which were named as the iron oxide copper gold or IOCG class of deposits, because the occurrence of such kind of mineralization in a granitoid in a continental interior was not known till that time. And so, the plan of this deposits plan is shown here. This granite is shown as the Roxby Downs granite, within which there is a brexia complex occurring almost about 4 kilometers to 6 kilometer kind of area, and is essentially covered by later sediments, and the majority of the ore body is a lenticular subhorizontal within the interior of the brexia complex, and we will just see how this deposit how the mineralization is disposed in the subsurface from the subsurface section of this deposit. As you can see here, this is a cross section of the Olympic Dam deposit, where the brexia complex and the mineralization is shown, and this is the mid Proterozoic sequence of the granite and the mafic and felsic dikes, and this is the brexia zone which contains the mineralization. And if we look at the one of the ore body in its subsurface section, it will get a clearer idea as to what the mineralization is like. There is clearly the mineralization, a richer mineralization of copper in form of bornite, it straddles the lower grade or the chalcopyrite zone, and the uranium mineralization is pretty distinct and is not it occurs separately as the ore body in the upper part, and so this cross section. So, this deposit led to a lot of speculation about what could be the origin of this deposit. So, the fluid characteristics does not indicate a very clear cut direct magmatic source, but there is the from the temperature and salinity value of this fluid that gave rise to this Olympic dam deposit does indicate that there has been involvement of more than one type of fluid in giving rise to this mineralization. The popularly held view is that it evolved by mixing of two fluids, one which is an oxidized fluid with sulphate. Essentially this occurrence of this hematite rich brexia. This brexia is essentially the hematite rich brexia in which the mineralization occurs. The copper mineralization occurs within the brexia complex, essentially constitutes of contains hematite along with fragments of the granite, and so this in itself is a distinct type which is different from the porphyry type deposits or any of the skarn type of mineralization. In the most simple term, possibly it could be thought of as some kind of an epithermal system, but it does not have any such kind of alteration zones as we see in the porphyry copper deposit. And the discovery of this deposit led to a elaborate program of exploration such and many they were discovered in many other areas in the world, and they go by this individual classes IOCG type of deposits and exemplified and typified by this Olympic dam deposit, which is almost unique in its mode of occurrence and most of its characteristics. Okay. So, that brings us to a discussion, to a close of a discussion where we were mostly dealing with hydrothermal systems which were associated with directly or indirectly with felsic intrusives and deeper sources as metamorphic fluid, and we saw the characteristics of such kind of deposits briefly without getting into much of the details of the genesis of such deposits. Now, we would like to go over to a very interesting class of deposits which are essentially known as the epithermal deposits in young volcanic islands. We have been seeing through such kind of maps that this is the Pacific Ring of Fire, and the deposits which we are going to discuss now are distributed all around this of the Pacific plate, or what is basically known as the Pacific Ring of Fire. The important ones we could see here, just about near the Papua New Guinea island, there is one small island which is Lihir Island, which holds a very rich important gold deposit. There is the Ladolam deposit. All along, if we see the Japanese island arc, here there are some deposits like this. In the Kyushu province, this is the Hishikari deposit, one of the very rich gold deposit, and in the western margin of this South American continent and the Western American Cordillera, we get series of such deposits which also are associated with, well, essentially, so they are epithermal. Epithermal essentially mean that they are confined to the top 5 km within the Earth's crust, means the active ore forming process is within that kind of a depth range, as compared to many of the hydrothermal systems which we have discussed so far are deep seated. So, these are the near surface operating hydrothermal systems. So, here as you can expect that the young volcanic islands are definitely responsible for formation of such kind of deposits. So, as far as this particular class, which are the epithermal deposits in the young volcanic islands are concerned, these deposits are broadly classified into two types. The one are the low sulfidation type and the high sulfidation type. On this diagram, the ones which are with open circles or open square are the high sulfidation ones, and the closed circles and the closed squares are the low sulfidation ones. As you could see here that these low sulfidation are the high sulfidation ones which are occurring in the Andean Chilean Andes in the south in the western margin of South American continent is very closely spatially associated with porphyry copper deposits. So, that means they must be having some common parentage as far as the mineralization process is concerned, and in most such deposits it is observed that they do have a very close time relationship. They are mostly synchronous or at the same time as formation of these porphyry copper deposits, which themselves are very young. Deposits such as Ladulam, which is almost about 400,000 years old, means 0.4 million years old. So, these deposits and the processes, they give us ample scope to understand the hydrothermal ore forming process. We can call them almost as present day ore forming systems. So, the distinction based on the classification as the low sulfidation and high sulfidation is essentially based on the oxidation state of sulfur. The sulfur is mostly in the +6 state here, and actually the classification based on the ratio of sulfur to chalcophile metals. It is not exactly that they do contain a lot of sulfur, but the deposits there essentially they have a high sulfur versus chalcophile metals, and their sulfidation state is higher, means as expected the high sulfidation deposits are likely to be dominated by mineralogy which are pyrite or bornite mineralogy, and whereas the low sulfidation ones will be pyrrhotite arsenopyrite dominated mineralogy, and they do have also characteristically the high sulfidation deposits are essentially of very low going to low pH, and their alteration characteristics are accordingly reflected in the alteration zones compared to the low sulfidation deposits. High sulfidation deposits are dominantly of base metals like copper, and the low sulfidation deposits dominantly are for the precious metals like gold and silver, although they will have some trace of the each in the other. And what is more interesting is that the low sulfidation in a similar geological terrain like Japanese island arc can have, as you can see from the legends here, both can have the low sulfidation and high sulfidation deposits. So, it would be expected that occurrence of the low sulfidation or high sulfidation has some local controls, although broadly the kind of volcanism or the composition of the host rocks would look to be more or less similar. Here is a cross section of, so you will just briefly look into the characteristics of these high sulfidation and the low sulfidation deposits. To the left is a cross section of a high sulfidation deposit, where it is observed that the deposits they occur to very close to the volcanic center. This is an example of one high sulfidation deposit in Philippines, where the porphyry deposit in the close vicinity is also shown, and the way the migration path of the fluid and the temperature, decreasing trend of the temperature is shown. So, they are less than about a kilometer within the volcanic center, and their depth range is about within 1.5 to 2 kilometers from the surface. This is a classic example, and they are sometimes associated with brexia. And interestingly, so these ore bodies do have an inverted teardrop type of shape, and they are essentially associated with something which is a very interesting feature, which is a residual of the Vagi silica, which indicates that before the mineralization episode, the fluid which interacted with the within these particular zones was extremely acidic in its nature, and it almost dissolved out the rest of the component, just leaving behind the Vagi silica zone. And this later on the the metals were deposited as metal sulfide in this acid, in this vuggy silica zone, that this basically is the mineralized zone, and they are surrounded by the alteration which is advanced argillic alteration, which is alunite bearing, advanced alunite and kaolinite bearing advanced argillic alteration, and with peripheral argillic and propylitic kind of unaltered situation also is observed. So, they are very much typified by very low pH conditions, giving rise to alunite in the alteration zone of the advanced argillic alteration. The hydrothermal breccias coincide with the ore zone, and here this kind of brecciation within the mineralized zone does indicate that there must have been some boiling of the fluid which caused the hydrofracturing and formation of the breccia. And this is kind of a thing which you can as a model for the origin of the high sulfidation deposits, setting of an acid alteration and high sulfidation ore formation, and ore forms with. So, here this zone is the formation of the ore, and this is the crater lag, and the temperature contours are shown, and as we could see here, the ore fluid generally is of a high saline. Below this there is a zone which defines the fluid characteristics to be of higher concentration brines compared to the ones which is causing the mineralization by effectively by dilution by meteoric water during the process of mineralization. So, this deposition is response to mixing of meteoric fluid with acid gas rich fluid rising from underlying magma chamber. The magma chamber is responsible in providing the very acidic some sulphurous vapor that condenses into the meteoric fluid and becomes very acidic in its nature, sulphate rich, and cause the alteration, alunite type of alteration, and they are very typical of the high sulfidation deposits. So, we will continue discussing about the epithermal deposit in young volcanic islands. Thank you.